Hey everyone, welcome to EDUx Talks. Today we're starting a brand new series, Questions No One Knows the Answers to. This is part 1. Think of this as a long walk at night under a sky full of stars. We're not here to conquer the cosmos, we're here to wonder about it. And when I say no one knows, I mean there's no consensus answer yet. Not that we're clueless, but that the frontier is still open. Pick your favorite question as we go and drop it in the comments. I'll feature some of them in part 2. Let's dive in. Question 1. Why is there something rather than nothing? This one sounds simple until you try to think it through. Why is there a universe at all? Why is there existence instead of absolute nothingness? No space, no time, no laws, not even possibility. Some physicists say that nothing is unstable, that quantum fields can fluctuate into existence, but that's not really nothing. That's a stage with rules already written. Others propose that the laws of logic themselves might entail existence, or that every possible reality exists somewhere, so of course at least one of them looks like ours. And then there's the unsettling thought that we've smuggled in the very thing we were trying to explain. The law that says nothing is unstable is still a law, so the puzzle remains. If you could ask reality a single question, would it be this one? Question 2. What, if anything, came before the Big Bang? We say the universe began 13.8 billion years ago, but the word before might be meaningless if time itself began with the Big Bang. Still, we can't help asking, did our universe emerge from a previous one in a cosmic bounce? Were there cycles of expansion and contraction? Did it bud off from a bigger multiverse like a bubble in foam? Did the universe have a no-boundary beginning, where time gradually morphs from a spatial direction the way a globe has no sharp edge at the South Pole? The truth is, our current math breaks down at the earliest moments. We have ideas, quantum gravity candidates like loop quantum cosmology, string-inspired scenarios, ekpyrotic models, but no decisive evidence yet. If before doesn't exist, our intuition might be the thing that needs rebooting. Question 3. What is time really? We live inside time. We're carried by it. But what is it? Physics sometimes treats time as just another dimension, like a road you can map, but not necessarily flow through. In that view, past, present, and future all exist in a block universe, and the sense of flow is a feature of our minds. Yet our experience screams that the present is special. The arrow of time, the fact that eggs break but don't unbreak, seems to come from the universe's low entropy beginning. Why did the early universe start in such an improbably ordered state? Also, in some equations of quantum gravity, time doesn't even appear. As if the universe is a timeless whole and time is a story we tell inside it. Maybe time emerges from entanglement. Maybe memory and thermodynamics weave it for us. But until we reconcile our equations with our experience, time keeps its secrets. Question 4. What is most of the universe made of? The stuff you and I are made of, atoms, stars, everything we can see, adds up to about 5% of the universe. The rest appears to be dark matter and dark energy. Dark matter tugs on galaxies, bends light, and seeds structure, yet it's invisible and slips through us like a ghost. We've chased WIMPs, axions, sterile neutrinos, we've built ultra-sensitive detectors deep underground, and so far, silence. Dark energy is stranger still. The universe isn't just expanding, it's accelerating, as if space itself has a small, persistent push. Is that a cosmological constant? A new field? Something evolving over time? We measure it, we map it, but we don't truly know what it is. When your cosmic pie chart is mostly mystery, you have to admit, our universe has a poker face. Question 5. What is the ultimate fate of the cosmos? Will everything wind down into darkness, a heat death where stars fade, black holes evaporate, and even atoms decay? Will space rip apart in a big rip if dark energy grows stronger over time? Could a quantum event trigger a vacuum decay, rewriting the laws of physics at the speed of light with no warning? Or, less dramatically, will the cosmos drift forever into cold and quiet? Our answer depends on the exact nature of dark energy and the deep stability of a vacuum. We can project timelines trillions of years long, but ultimately our predictions rest on unknowns. It's a strange feeling to live in a story whose ending we can't read. Question 6. What is consciousness? You can measure brain activity, map circuits, and simulate neurons. You can build machines that recognize faces, compose music, and beat champions at strategy games. But there's still a hard problem. Why is there something it feels like to be you? Why is there a first-person experience, color, pain, the taste of mango, at all? Some theories say consciousness emerges when information is integrated in particular ways. Others say it's a global workspace broadcasting information across the brain. Some philosophers argue that consciousness is fundamental, woven into the fabric of reality in tiny amounts everywhere. Others think it's an illusion, a clever trick the brain plays on itself. Yet we wake up every day inside it, certain of it, and science is still figuring out how to measure, compare, and explain it. Whatever consciousness is, the fact that it's asking about itself is one of the strangest facts in the universe. Question 7. Do we have free will? If the universe is governed by laws, then aren't we just billiard balls on a cosmic table reacting to prior causes? And if quantum randomness injects unpredictability, does that give us control or just noise? Neuroscience shows decisions forming in the brain before we're aware of them, but awareness and decision-making are a dance, not a single spark. Philosophy offers a middle path called compatibilism. Maybe free will isn't about magic escape from causality, but about acting according to your reasons, your values, without external coercion. That still leaves a haunting question. How do you choose your reasons? We live as if we're responsible for our choices. Society depends on it. But whether freedom is fundamental, emergent, or illusory remains open. Question 8. Why is mathematics so unreasonably effective at describing the universe? We invented math as a language of patterns, and yet math keeps predicting truths about reality that we haven't even observed yet. Complex numbers were a curiosity, then they became essential to quantum mechanics. Non-Euclidean geometry was abstract, then it became the language of gravity. Is math discovered, out there, waiting for minds to find it, or invented, a creation that somehow aligns with the world? Maybe the universe is fundamentally mathematical. Maybe our brains evolved to exploit the patterns that actually exist, and math is the ultimate pattern machine. Or maybe it's a cosmic coincidence that our best map feels like the territory. Either way, math is the spellbook we use to talk to the universe. Why it works so well is still a mystery. Question 9. Are we alone in the universe? There are more stars than grains of sand on Earth, and many of those stars have planets. It seems almost inevitable that life exists elsewhere. And yet, where is everyone? This tension is called the Fermi paradox. Maybe life is rare because the jump from chemistry to biology is incredibly improbable. Maybe intelligent life is common, but the steps from intelligence to long-lived technology are brutally difficult. Maybe there's a great filter, a barrier most civilizations never cross, either behind us or ahead of us. Maybe advanced civilizations stay quiet, hiding in a cosmic, dark forest. Or maybe the distances are just too vast, the signals too faint, the timescales misaligned. Right now, we're scanning exoplanet atmospheres, listening for signals and looking for biosignatures. But until we find a second spark, we don't know if we're early, lucky, or completely average. Question 10. How did life begin on Earth? We can trace life back billions of years, but the first step from non-life to life is still foggy. Did life begin in deep-sea hydrothermal vents where chemistry thrives on gradients of energy? In shallow ponds that concentrate molecules and bake them in cycles? Did RNA come first, acting as a molecule that both stores information and catalyzes reactions? Or did metabolism come first, with networks of reactions that eventually learned to store a blueprint? We've made protocells in the lab that can grow, divide, and even evolve in simple ways. We've stitched together pieces of plausible prebiotic chemistry. And we found organic molecules in space, on comets, on Mars. But the exact path, the first real living system with heredity and metabolism, remains out of reach. It's the ultimate origin story, still unwritten.
Question 11. What's really going on in quantum measurement? In quantum mechanics, particles aren't here or there until we measure them. They exist in a cloud of possibilities described by a wave function. When we look, the cloud collapses to a definite outcome. But what does that mean? Is collapse a real physical process? Is it just our knowledge updating? Do all outcomes happen in parallel universes and we just find ourselves in one branch? Does the universe have hidden variables guiding outcomes in a non-local way? Decoherence explains why quantum strangeness hides at large scales, but it doesn't explain why a single result happens. The equations that predict experiments perfectly leave the interpretation up for grabs. The theory works like a charm, and yet we're not sure what, if anything, it's telling us about what's real. Question 12. Are there other universes? There are several roads to the multiverse. Inflation, the rapid expansion at the beginning of our universe, might create endless bubbles, each with different properties. Quantum mechanics might branch reality into many worlds. Some versions of string theory suggest a vast landscape of possible universes with different constants. But how do you test a universe you can't visit? Maybe there are subtle fingerprints, collisions between bubbles, unusual patterns in the cosmic microwave background, statistical clues in the distribution of constants. Or maybe the multiverse is a philosophical move, not a scientific one, at least for now. Either way, the idea tempts us. Our universe might not be the whole story. Question 13. Why do the constants of nature have the values they do? Change a few numbers, the strength of gravity, the charge of the electron, the density of dark energy, and you could get a universe with no stars, no chemistry, no life. That looks like fine-tuning. Are we seeing an illusion, like a fisherman who always catches fish bigger than his net? Of course, we find ourselves in a universe compatible with our existence. We couldn't be in the other kind, but is that all there is to it? Maybe there's a deeper theory that pins these values necessarily. Maybe there are countless universes with different constants, and we're just in a friendly one. Or maybe we've misread the situation entirely. Until we can derive those numbers from something fundamental, or find they can vary, we're left staring at the dials, wondering who set them and why. Question 14. What happens inside a black hole? And what happens to information? Cross the event horizon and, according to classical physics, nothing can escape. At the center, the equations predict a singularity, where density goes to infinity and our theories fail. Meanwhile, quantum mechanics insists that information can't be destroyed, but black holes evaporate via Hawking radiation. So where does the information go? Is it smeared on the horizon? Encoded in subtle correlations? Does space-time shapeshift so that the information slowly leaks out? Are there firewalls, searing curtains that break physics as we know it? Or is there a deep equivalence between geometry and entanglement, ER equals EPR, that ties space-time to the quantum threads of information? We can hear black holes collide through gravitational waves, but their interiors remain the most private rooms in the universe. Question 15. P versus NP. What's the nature of difficulty? Some problems are easy to check, but hard to solve. If I give you a completed Sudoku, you can verify it in seconds, but finding one from scratch can be brutal. P versus NP asks whether every problem whose solution can be quickly checked can also be quickly found. If the answer is yes, the impacts would be seismic. Cryptography as we know it could shatter, biology and logistics could leap forward, and 1,000 puzzles would surrender overnight. Most experts suspect the answer is no, but suspicion isn't proof. It's one of the biggest open questions in computer science, and it cuts to the heart of what it means to compute, to solve, to know. Question 16. What is infinity, really? And does the universe have it? Mathematics has different sizes of infinity. There's the countable infinity of whole numbers and the uncountable infinity of the real line. You can fill a hotel with infinitely many rooms and still make space for new guests by shifting everyone over one room. That's wildly counterintuitive. Physically, does infinity exist? Is space truly infinite or just very large? Are there infinitely many universes, or is the total number finite but enormous? Even inside math, some statements about infinity can't be proven or disproven from our standard axioms. They sit beyond our current foundations. Infinity is both a tool and a mirror. It shows us the limits of our intuition and maybe the limits of our logic. Question 17. Why are there 3 generations of particles, and why this pattern of forces? The standard model of particle physics is an impressive catalog: quarks and leptons in 3 families, forces mediated by bosons, and a Higgs field giving mass. But why these particles? Why these charges, spins, and masses? Why 3 generations and not 2 or 5? Why is the strong force so strong, the weak force so shy, and electromagnetism just right for chemistry? We can measure all of this to staggering precision, but we don't know why the menu looks this way. Is there a deeper symmetry hidden underneath? Are these parameters environmental accidents in a multiverse? Or is there a principle we haven't discovered that makes the pattern inevitable? Question 18. What is the origin of the arrow of time? We touched on this earlier, but it deserves its own spotlight. The second law of thermodynamics says entropy tends to increase. That gives time its arrow. Memories form in one direction, we age, eggs break. But if the underlying laws are reversible, why should entropy have started low? Why didn't the universe begin in a high entropy state and stay messy forever? Some ideas suggest that the universe was born smooth and simple. Others imagine time-symmetric cosmologies where entropy grows in both directions from a low entropy bounce. Until we explain that initial order or show why it wasn't special, we're missing a crucial piece of the time puzzle. Before we wrap, I want to ask you something important. Which of these questions changes how you see your day? The best mysteries aren't just trivia. They sneak into your morning coffee, your commute, your conversations. They make you more curious, more patient with uncertainty, more alive to wonder. If one of these grabbed you, time, consciousness, the multiverse, tell me why. Your reasoning might spark someone else's. And here's a thought as we close part 1. Questions like these do something powerful. They pull disciplines together. Physics meets philosophy at the foundations of time. Biology meets chemistry in the origin of life. Computer science meets logic in P versus NP. We learn the most when we let these borders dissolve and let curiosity take the lead.